And we did this example last time. So, as always, remember, you can check by differentiating the result and seeing what's going to happen. And we did. We differentiated. It matched with what was inside of the integral, so we did not mess up. Let's do one more example. Let's do many more examples. Your substitution is like product rule or chain rule. You just keep doing more and more and more. This time I will show you my notation. My notation is a little bit different from what you saw here. And then students choose the one they like more. Many students choose this notation, they like it more this way. I will show you what I like. So, what do I like? Integral of, in the denominator, 3x cubed minus 4 dx time, and in the numerator, let's do 9x squared. Why not? Let's do that. 9x squared. How to integrate a quotient. In Calculus 2, we teach more techniques of integration of the quotient. But in this case, you should kind of see, wait, I think one part of the quotient looks like derivative of another part. Specifically, 3x cubed minus 4, when you differentiate, gives you 9x squared. It's indeed true. Even if I put this part, 19, it still looks close to it. And whatever close to it is good enough. And also, I don't like having something complicated in a denominator. So that's also a good motivation to call the denominator u. You are the one who are choosing what is u. That's a creative part of the integration in general. You choose. So this is how I see problems like this. Let u be 3x cubed minus 4. Now, you still did not get used to it, but you should slowly. We're still going to have one quiz at some point. Quiz number 11. Well, the moment you chose u, you need to find du. Why? Because dx have to be substituted with some kind of part of du. So we immediately differentiate that part. It gives you 9x squared, and then dx pops out. Because you're differentiating with respect to x, dx pops out. Last time I was teaching you, you solve for dx and plug it here. That makes sense. This time, I will not do it. Students usually like solving, actually it's more explicit for them. But I will show you the way I see it. I see it this way. In the integral, the denominator will be u. This is my du. I even would say like this. My du is 9x squared dx. But I have it literally over here. So why not to call this du right away? And you don't have to solve for dx and plug it in. If you solve for dx, don't have to write this down. Dx will be divided by 9x squared du over 9x squared, which will cancel out with this 9x squared. Yes. So why not to just call the part that matches the derivative, the whole du, since it matches it anyway. Like so. Here it is. The integral becomes, what do you think is the integral?
1 over u.
1 over u, and then where is my du?
Du.
Just du. Or in this case, I would even say it's du over u. It's the same thing, you're correct actually.
Wait, why is it y1?
Yeah, I will show you why one in a second. I would see like this. du is the blue part in the numerator. U is what we chose to substitute in the denominator because we don't like denominator. We changed, we did some kind of thing going on, and then now it's du over u. Agree on this part? Du over u. What is the integral of du over u? If you don't know, rewrite it just like you mentioned as 1 over u times du. Now you know this integral. You see, I just taken it out. So 1 over u times du. Does that make sense? What is the integral of 1 over u times du? ln. I'll put equal sign and I'll go below the box. ln of u plus c. Correct or not?
Yes. I mean, you have to...
Something missing. Something is missing. Absolute value, don't forget about that. U might end up to be negative, and you cannot have negative of ln. Your computer code will tell you the error, and it will never explain you why. Java doesn't explain. It says there's an error. You as a mathematician have to fix it yourself. Last step left. Should we keep it as the answer? No. Nobody knows what u is except you. You use it as a tool that helps you to solve the integral. So don't forget to plug it back. If this was like a 5 pages long integral, it's nice to actually write it down over here for the reader to know what is happening. The reader is reading your work, say another scientist from another class or lab, and you say, oh, u is actually 3x cubed minus 4. I chose it like this from the beginning. And then you will be like, oh, that's why u disappeared. And you have now 3x cubed minus 4 inside of the u. Many students, they plug it in right away, so you don't have to actually have this step extra. So it's ln of 3x cubed minus 4 plus c. Ask me. Yes, good moment to ask.
My biggest question is, it feels like we should, I'm a little confused with steps. Wouldn't we need to undo the quotient rule?
This was not a quotient rule. We will be doing quotient rule actually next week.
Oh, I guess because...
This is chain rule where one part is derivative of another part. Let's check if that's true. How do we check, people? Who knows?
I'm just confused with the three falls.
How do we check? Differentiate whatever is in the box. Let's find derivative of 3x cubed minus 4 plus c prime. Derivative of log is 1 over everything inside. Agree? Times the derivative of the function inside. The function inside is 3x cubed minus 4 times derivative of that is 9x squared plus c gives you 0. Is this the function inside of the integral? Yes. So we did good.
I'm just confused as to how we got here.
With u substitution. We're going to do more, you will see how it works. Idea is, step 1, choose the part you don't like to be u and hope for the best. That's just a funny recommendation, but actually that's how it works. Intuitionally, you see one part is derivative of another part, but usually it's a pure guess. You just guess something and it works. Step B, find du, plug it in. Step 3, if you were able to integrate, you did good. If you're stuck on the moment over here, if you cannot integrate this integral, whatever you did not help you. So you have to go back and figure out another u substitution. And that's how it's a creative process of being stubborn and very frustrated. Yes?
So you say like you kind of just pick u and guess, like if you were to pick 9x squared, you would be wrong, right?
So let's try. It's exactly what I'm saying. Very good question. Let's try another one. How did I know which one to pick? As a scientist, you look at the formula or number of bacteria and you're like, wow, this will definitely blow up. Or like, oh no, this is asymptotic. How do you know all those things? Usually from experience. And that's why it's hard to explain. But in this case, intuition told me that A, whatever is in denominator will be hard to integrate, so at least that should be easy. Let's make that u in the denominator because denominator is hard to integrate. So that's kind of how I think about this. I don't like denominator, let's call it u. But if I choose u to be 9x squared, du will be 18x dx. This will be u, dx will be changed, but this one does not go away anywhere. And you end up to have still complicated denominator which did not go away and did not become simple. And that's how you know you're stuck. Make sense? So you try and you're stuck. While here, when you differentiated it, you need to learn that, oh, this blue part is perfectly my numerator. So everything got converted into u, and that's the goal. The moment you converted into u, integral became easier. You integrated it and then went back to the original notation.
I think I get it now.
Do we just use a higher? Do we just use u as a higher exponent?
I wanted to say it, but I avoided saying it. Sometimes the case is when it doesn't work either. His suggestion is not just maybe to notice that cube, x cubed, choose that versus x squared. It's a creative process. In this case, yeah. But I would say seeing denominator as a bad guy is more practical. Denominator, everything inside of sine, you know, what is sine of x squared minus 4? Yeah, we don't like sine to have something complicated. Let's call that u, and so on. So that actually works better, usually.
Is there an example where choosing the higher exponent is a mistake?
Yeah, usually with fraction actually, but I can show you later if I found. Very good too. You have good imagination. So how about this one? Okay, now I will start asking you, what do you want to choose to be your u? Third example. Integral of 5 ln x over x dx. Boom. What do you think here? Why would you choose ln x to be u? I don't like denominator. Maybe u should be x then.
Because that's when you differentiate ln x, you get 1 over x.
Exactly. You see, she sees the next step, and that's what I'm trying to explain you. See the next step. When you differentiate x, it will give you 1. That's not helpful at all. When you differentiate ln x, it gives you 1 over x, and it's there. And that's how, like, the next step gives you a hint. So when I differentiate something, is it even helpful? Is it there to substitute something to make it easier? So let's try. If I choose this to be u, do you see that dx over x will be my perfect du? So think about that. Like this kind of, let me isolate this example, like so. If ln x is u, then dx divided by x will be du. Let's check. Let u be ln x. Then differentiate right away. ln x gives you 1 over x dx, but we have it in the integral. If you don't see it, you can write it down like so. I would kick out 5. That's not necessary, but I like it. I'll write down ln x times dx over x. This is also not necessary. Usually people don't rewrite it. They just see it. They just see it. That, oh, now it's very visual. That this is u, and this is perfect du. Do you agree? So from this box, I don't even have to solve for dx. These get plugged in, and these get plugged in. This integral becomes a very complicated integral. Tell me, what is it? 5 integral of what? U du. That's like literally the first integral we ever learned how to do. Integral of x dx. U square over 2. It was a joke when I said it was complicated. I forgot to change intonation, so maybe they did not understand. What do you think? Before we finish, I want to, like, this is what U substitution is. You kind of have to see 2 steps. One, which one should I choose? And then before you write it down, maybe like, so what is derivative of that? Is it even helpful? And U substitution works when one part in the integral is a derivative, more or less. Maybe divided by 5, multiplied by 7. A derivative of another part. So that's how you know. And then you try and fail. Maybe you could choose 1 over x to be u. That will make it even harder because du will be minus 1 over x squared dx. That does not help at all. So you kind of like try and fail, and that's how you know when it works. What do you think?
So what you're saying is it doesn't work in this case?
Huh?
So you're saying U substitution is not a productive way to solve this problem?
No, this one actually, this is perfectly a substitution problem.
See, I'm confused because how do we finally solve this?
Oh, we did not finish. I just wanted to ask questions, if people have questions on this.
Sorry.
5, what is the integral of u du? U squared over 2. Do you allow me to substitute right away?
Yeah.
I would see it like this. It's u squared over u, but u is ln x. So it's ln x squared over 2. You can check right now while I'm talking if you want. By differentiating it. 2 goes down, cancels out with 1/2. ln will stay times derivative of ln is 1 over x. And it becomes again 5 ln x times 1 over x dx. So it matches. If you mess up, you can differentiate and you'll see it doesn't match. So that's how you know. Yes?
Where did you get the square?
Oh, the square. Yeah, that's why I was afraid if I should skip or not. Let's do it this way. I will not skip then. 5 u squared over 2, right?
Oh, the
Integral. Yeah. That's why I was afraid to skip. Integral u squared over 2. And then sometimes we're going to give you some nasty functions like arcsine and so on. You don't want to rewrite them every time. What if your u is like 5x cubed minus 3x plus 7.3? You don't want to rewrite it so many times. So many students realizing that just plug it right away. You don't want to write it so often. Check. And it works well. More. This one's again. I will go slow and then you guys have to help me. And it's very satisfying because it's working well all the time, so it's really good. Integral of cosine x. Let's do some trigonometric functions. E to the sine x dx. So again, I like to make this joke. Any of you watched the movie The Matrix? My childhood movie, my favorite movie, right? In the matrix, okay, I have to show you. In the matrix, they were doing like this. Oh, the Neo is the chosen. It's always like the chosen one, right? And the most popular picture from the matrix is this one. When he looks at this wall of dropping numbers and he sees things there, right? So he looks at this and he sees that this is actually a human or this is actually a bird. And this is what we become as mathematicians at the upper level classes. We look at I make this joke that we are chosen one, but to be honest, lots of practice gives you this idea. You look at this and you immediately know that it's going to be e to the u du. Do you know? So like with experience, it becomes really cool. A huge long equation, and you can say, oh, this shrinks to 0. Why? Oh, don't you see the negative exponent? Because we learned exponential decrease function. Then, oh yeah, this thing is repetitive. And people are like, how do you know? But there is a sine and cosine over there, and they represent the repetition and cycling. So with experience in biology and medicine specifically, you already know how all this looks. Okay, let's do it.
The ability to explain things always follows the bell curve.
Yeah.
Your knowledge of it.
That's true, that's true. So,
Once you know it well enough, you will never be able to explain how you know.
that's a good point. So what do you think we should choose u? There's like 3 things here. Exponential, cosine, and sine. Choose. We have 3 choices.
What's it?
This one may be u, or this one may be u, or maybe this one is u. Sine, guess number 1. Any other guesses?
E sin x.
E sine, the whole thing, maybe is also u. More guesses? And the cosine is the last one. So let's practice from cosine. If I choose cosine to be u, the u will be minus sine, and we don't have it around. It's an exponent. If I choose e, derivative of e is still e, but we don't have more e's, so it will not go away. If I choose sine, derivative of sine is cosine dx, and it's standing over here, and that will be perfect. The other intuition, if you do not understand what I just said, it's okay. The other intuition works better. E to something, that is too hard. Let's have it e to the u. It always works, imagining that you don't want to make complicated things too complicated. When you have sine of something, that is too complicated. Intuition tells you, you know what? Sine of u is good enough. It's already hard to work with trigonometric functions. Let's not put any polynomial inside. Same here. It's already hard to work with exponential functions. Let's not put trigonometric in there. And that intuition helps a lot to recognize that this is a perfect choice for u. But let's see why. If u is, you see, I'm quitting writing any if and let, too much writing. And usually we just put a box. It's intermediate calculations, which we not even always show in our research. When people ask at the conference, I really like your results, how did you get it? We'll say, we did your substitution over here and some numerical analysis over there. Then they can approach after the conference and seek for details. But usually we don't show this at the conferences or talks. Du, derivative of sine, is cosine x dx, and this is my table. Either you solve for dx and plug in and cancel it with cosine, or it is better to see that this piece is a perfect du. Du is here. So, this piece. When I chose sine to be u, cosine x dx now immediately disappears and becomes du, which is much easier than to have trigonometrics everywhere. Now observe, we had 2 trigonometric functions. We're going to get rid of them both. It's going to be e to the u du. It's like the easiest integral you can imagine. See, we had 2 trigonometric functions, and because sine alternates with cosine when you differentiate them, you choose one of them, the other one shows up from du. You just need to be smart which one to choose, and the recommendation is you want to have e to something simple, choose that to be u. Yes?
Would it be negative cosine? Because like when you differentiate cosine, it's negative sine.
Derivative of cosine is minus sine, but u was differentiated, and u was sine. So you find derivative of your u. But you're right, if we choose this to be u, derivative will be minus sine. So it depends on your choice. Good question, yeah. What is the integral of e to the u? E to the u, I'm ready to substitute back right away. Sine x dx.
Don't you need to multiply?
Maybe it's too fast, so I will. Plus c, yes, thank you.
Don't you need-
Maybe it was too fast, so I will write down for you. E to the u is e to the u plus c. You copy the whole thing. And then you go back to the original function. That's a little bit too much writing, so usually students just plug it right away. And they recognize that it was e to the sine x plus c. Yes?
Don't you need to divide e by the derivative of sine x as well?
Let's check. I will do it this way now.
Or
He's,
by
yes? That's a very good question. Where did the cosine go, right? Let me do the check and then I will explain it because the check itself might click. Let's check if we lost cosine and if it got messed up. I will differentiate e to the sine x plus c. Sometimes some of your brains work the other way around, which is pretty cool actually. It's nice. Sometimes people like, I see the end of the story and now I'm building the beginning from the end. This is the end of the story. The derivative is the end of the story, of the integration. So I'm differentiating, copy the function, multiplying by the derivative of the function inside. That gives me cosine x, because derivative of sine is cosine. This is plus 0, is the function, which is exactly what we had inside. So we did not lose anything and we did not miss anything. Why did the cosine disappear? Cosine got swallowed or absorbed by du. When u was chosen to be sine, du became cosine and got renamed. It got renamed. Make sense?
it canceled out when you divided by when you divided e by cos x du or dx cos x dx, aka du.
Yes.
Du canceled out.
It canceled out, exactly. Chris is talking about this situation. Originally, I was teaching you that you solve for this dx. dx will be du over cosine x. Cosine x cancels out with cosine x. Students like this because it's very straightforward. That you solve, plug it in, it got canceled out. I don't prefer this way, but students do, so I show both. Europeans, we don't solve for dx. We actually taught to see the match and plug it in, while Americans are taught to solve for dx, plug it in, and cancel it out. So choose which one you prefer. I saw students liking both. So
Without seeing the intermediary step, it didn't make any sense to me.
let's do some this. This is interesting. What happens with u substitution when we work in this definite integrals? And that is the most interesting part here. That is the most interesting part. This is all actually shows us a transformation of the behavior of the functions, and that's why it's actually fun to explain. What happens with definite integrals? Definite integrals. Definite integrals have one extra step when you have to work with u substitution. Let's do the example right away and see how it works. Integral from 0 to 3. Definite integrals means the limits of integrations are defined. So we're going to do plug the top minus plug the bottom at the end. There's no plus c anymore. X plus 2 all over x squared plus 4x plus 7 dx. Like so. Okay, we did not do definite integrals before, but it looks the same thing we just had today. Let's choose your substitution and see how it goes. I'm saying choose your substitution because we're going to learn more techniques, and soon it will be up to you to choose integration by parts or u substitution. There are also more techniques we don't teach here, integration, substitution with trigonometric function and stuff like that. There are many techniques how to solve integrals. You guys are lucky we only teach you like 2, and they're the best ones. They're very practical. What would you say we should choose for you? Make a choice. Make an intellectual choice. Why did you say denominator? One guess is have higher degree. Good point. X squared has a higher degree than x, so differentiating will decrease the degree, and we have more chances that whatever is left will be the derivative.
Also, Chris said it's more complicated.
It's more complicated. Very good idea. I always tell you, choose complicated things to be you. It makes sense. In my master's degree research dissertation, I was working with 7 by 7 equations, and they did not fit when I was printing the work to submit it to the department, it did not actually these are matrices as well. That's what I was doing. They would not fit here. So what I did, I renamed everything that was too long with U, J, K, M, and sometimes we use the whole alphabet to do that. That's why you see A1, A2, A3 so often. I renamed everything, made it short, it fit on the page, and it was like, where? And then there's like 3 pages of explanation. U is this, V is that, D is that, DU is this, and so on. So it's a very common thing in biology and medicine because these formulas are also very long and clumsy, but they condense it with renaming complicated things with a small notation. And usually those notations are, they actually make sense. In epidemiology, P is population, P sub 0, initial population. R, recovered people from the disease. Let's see, I, infected people, and so on. So they actually make sense, those letters chosen for a reason. If this is U, let's see if it works. I'm choosing U to be x squared plus 4x plus 7. Again, let's one more time have this nice notation. Let U be this, then. Everything else comes from this choice you made. Then now there will be more things than just du. Du is derivative of u. Du is 2x plus 4. More or less. Yeah, don't forget dx.
Which is just 2, which is just 2.
Maybe like this. More or less, right? It's almost as x plus 2 dx, but I'm looking in the numerator and I just hope it would match. Then it will be du over u. That would be nice. Logarithmic function again. But it did not match, so what was your suggestion?
It was 2u.
It's just 2u. 2 du, yeah. Maybe,
2.
right? Since it's x plus 2 and we have 2x plus 4, maybe let's factor out 2. It will be x plus 2 dx. So as you can see, there's no strict rule about it. It's more like working on it and making sense out of what you're doing. The goal is to substitute this whole thing with du, but it did not match. So probably we'll have to multiply or divide by something. So here, it will actually be good for you if you solve for dx in this case and see what's going to happen. Let's solve for dx. dx is, how do you guys solve for dx? We're dividing by 2x plus 2, right? So it will be du, let's zoom in, du over 2x plus 2, like so. And we are going to plug in equation number 1. We don't do 2, we don't do 3. And equation number 4, we'll be plugging these 2 equations, number 1 and number 4, into the integral. Number 1 is over here, it's u. Number 4 is over here, x plus 2 dx. Let's plug dx into the integral. Don't write limits of integration yet. That's a different story. I have to finish that. Denominator is u. That's the only easy part here. We chose it to be u, so we know it's u. Dx is, so we don't, this one is still x plus 2. But dx is substituted with, let's put it in blue color, du over 2x plus 2. And this is what we wanted to happen. This part got cancelled out because one part of the integral was derivative of another part of the integral. Make sense? So the integral became exactly what we hoped it to be. Almost exactly. It is integral. Oh, actually, don't write below. There's still something to write over here. It's actually integral of du over u. But what is 1 over 2? Let's put it in front. Because numerator was twice smaller, so that's then the dx, and then the du. So that's why this 1/2 popped out. It's over here. Let me write down it for you. It's over here. Dividing by 2 means multiplying by 1/2. You can even put it over here if you want, but not necessary. Ask me before I move on, because that's not the end. We actually do need to do extra work. What do you think? Then, you know what's wrong here? I cannot put 0 and 3. Can anyone explain why I cannot put 0 and 3?
Because they're for x, not for u.
Therefore, x. In some literature, you will see notation x equals 0 and x equals 3, but we cannot have x equals 0 and x equals 3 for the integral in terms of u. It's du at the end. Du means, so the integral phrasing means integral of the function, with respect to the variable u when u is running from 2, but that's not u running. So we have to figure that part, apparently. That is not correct. And that's why continuation is happening over here in the table. This table will have one more step extra because it's a definite integral. You have to change limits of integration. It's actually fun. Students usually like it. When x is 0, that is the lower bound.
7.
How did you get 7? Literally out of nowhere.
You, I didn't get them.
I know. I'm just wanting you to explain it.
I don't know why you haven't asked me.
I like to guess like 7. I like actually making like random numbers in class and people like, what? X, when? I will do like this. When x equals 0, u will be. I don't know. But what I do know is my u choice. Oops. U is x squared plus 4x plus 7, remember? That's equation number 1. Maybe I can write it down. Equation number 1 tells me that my choice was x squared plus 4x plus 7. So I just plug 0. And guess what the answer? 7. Good job. And this is how I immediately can write down that 0 got converted into, let me change the blue color, 7.
Well, instead of converting things, can't we just plug in their x back in and it's solved?
Yes. So, spoiler alert, yes, you can. I will show it in a second. Very good point. And it's easier, to be honest, so many people like it. When x is, what was the other bound? 3? U is, and nobody writes it down so slowly, so you just calculate. 3 squared is 9 plus 3 times 4, 12 plus 7. What is that? 28. There is also nice notation. You will see Europeans like it. We usually write it like this: 0 becomes 7, 3 becomes 28. So we like it like this, and we know that it's U substitution. So 0 became 7, 3 becomes 28. Now this integral makes sense. This integral is in terms of u, where u is running from 7 to 28, from 7 to 28. So see how interesting it is. We transformed the integral of x, function of x. It was a ratio of two polynomials, x plus 2 over x squared plus 4x plus 7. With respect to x, when x is running from 0 to 3 into the completely new integral, which is du over u times 1/2 from 7 to 28. That is called a transformation. Before we finish the integral, I want to explain it this way. Students always like when I do that. Transformation is this. I was working with the complicated integral. Integral represents some area. Double integral represents volume and density of the liquid here and so on. So this was the volume or liquid in the bottle. And it was described as x plus 2 over blah, 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 from 0 to 3. I don't know how much is it. I'm looking at it, there's no marks. I don't understand. It's not full, so I cannot just check how full it is. Instead, I'm taking a measuring cup, right? I know how big this bottle is. It's made with a very fixed size. Or say it's a measuring cup. What I'm gonna do is, I'm not gonna do that, but I will open and fill in this liquid into the measuring cup. Leave it alone. Now I have completely new shape. It's an integral from 7 to 28 in terms of completely new variable. It's very different. But the answer is the same. The amount of liquid is the same, but this integral is easier. This shape is easy. It has measuring here, it's a measuring cup, and like, oh, it's a quarter of the liter. And that's the answer. And when they ask me, but wait, you had it over here, how come you gave it the answer? I said, yes, I used a measuring cup. And U substitution is a measuring cup. It's a transformation of the complicated integral into a simple one, giving you the same answer. Does that make sense? U substitution is a transformation of one object into another one, saving the property like the amount of liquid or mass should be the same. You took mass from the box, put it on the weight. Now you can see the answer, transformation. And that's why limits of integration were changed. This was completely different. Just a second before I ask you to ask a question. In this bottle, it's so big. It was from here to here. In this bottle, probably it will be much higher from here to here. And that's why from 0 to 3, it became from 7 to 28, because the shape of the measuring cup is different. And I'll show you this on the graph, and you'll be fascinated at how cool is this idea. Yes?
I'm just confused, like, what makes this problem different from the other ones, like, in line cup.
Oh, you have to do it because I don't know how to integrate. Yeah, this is a very good question. Why are we even doing that? Because I don't know how to integrate x plus 2 over x squared plus 4x. The whole point is to integrate, and we don't know how to do it.
So we always, when it's a separate problem, we have to transform?
If we don't know, yeah. Very good question, actually. She's asking, we don't know how to integrate. Do we always do U substitution? No, we can have lots of different ways to do it. In this case, we teach U substitution, so all the examples in this chapter can be done by U substitution. On Monday, we're going to learn one more, and finally, in upper level classes, we teach you how to use computers to do it. The last resort, when you have an integral in front of you, I can actually show you. The integral in front of you, which you don't know how to integrate, don't forget we did not finish the problem. Why this is opening, going. When you don't know how to integrate something, let's do integrate, I don't know, just give me something crazy. X squared over arc sine of ln x minus cosine x from, I just even indefinitely, you know, just let's try that. Look at this, and it's pretty short integral actually. If you don't know how to integrate that, let's see if it knows. Oh, it did. If you don't know how to integrate that, use some kind of tools. One of the tools is U substitution. You're lucky if you can use that one. That is the basic one. One we're going to learn on Monday. There's more and more and more. And if none of them work, the last resort, I ask students usually, what do you think you will do if you cannot integrate, but you're paid 6 digits to do that? Your salary is amazing because they believe you can do it. What would you do? What do you think? Students usually say, like, I would Google. Yeah, if everything can be Googleable, why you're paid 6 digits then? Right?
Maybe guess the answer.
What? Because you know how to go. Everyone knows how. Even my grandfather learned how to Google. Okay.
Maybe guess the answer and then work from. Like,
very interesting. Guessing the answer. Sometimes people do that. The last resort is to ask a computer to approximate the answer. So this one is my guess. You see, it's not an exact answer. It's not something plus c. It's an exact. It's some kind of approximation. Because computer know how to approximate things, and we teach in different classes how to do that. So last resort is to feed it into computer, like Wolfram Alpha, and saying, do your best. And sometimes it takes 24 hours for one integral to be solved. So in PhD, we do that. We feed computer with lots of stuff. Space science with math, that takes a week to compilate one integral or system of integrals. So sometimes it takes lots of time, and that's not practical at all. And that's why it's getting interesting. Sometimes it's not that hard. Let's see this one. If it's just arcsine of log, still doesn't like it. But if it's this one, then it should be fine. See, did it. So, depends. Let's finish now. I'll show you the two graphs comparison, and you will see what this transformation means. So, let's see. Integral of 1/2 du over u is what? 1/2 stays. Du over u becomes ln absolute value of u, a bar from 7 to 28. What is new just happened from what we did before? We do not go back to the original value. We do not go back to x. We don't have to. And that's why it's different from indefinite integral. The question was how much liquid was in this awkward shaped bottle. They never cared what functions I'm using to check that. So I'm finding any bottle I have. Maybe I don't have a measuring cup, but I have this one. I check how big this cup is, and it tells me, oh, it's 1/2 of a liter. I'm like, fine, it's better than nothing. I pour it here, and I say the answer. And the answer will be 1/2 ln of 28 minus 1/2 ln of 7. And this is the final answer. And we never came back to the original bottle anymore. When I poured this liquid into the new one, I never had to go back. And that's the idea of a definite integral. Since it's the answer, it's the number, you don't have to go back. Just make sure that everything matches. If this is u, these guys also should be in terms of u. That is important. So the answer is a number. It's a positive number, by the way. Yes?
Where did du go?
Du, where did it go?
Yeah.
So when you finish integrating a function, right? You get some kind of result plus c, du disappears. Same with a definite integral. The moment you have definite integral, instead of plus c in du, you put bar, like so.
I guess it would.
Du and integral sign disappears when you actually finish integrating.
That's doesn't work.
Okay, so basically, I think again now. It's so easy for me to look at the x and the u.
Yeah. A variable.
Or not as variables, but I have to look at them as variables sometimes, and there are times I have to look at them as just a sign to indicate the end of integration.
So let me tell you what I'm talking about, the transformation. We were asked to find the area below this function, which was x plus 3 over, oh, there's some example here, x plus 3 over a quadratic function, x squared plus 4x plus 7. Remember that the definite integral represents the area from 3 to 0. So I'm plotting this. Here is the function. They asked us, let me do this. Are you guys having a question? Ask me if you have a question. We were asked to find the area below this curve. Remember that integral represents integral from 0 to 3, right? Represents the area. Here's 0. 3 did not fit. It's over here. We were supposed to find this area. And this is what I'm telling you. We don't know this area. It's hard to find it. How would you find it? So what I did, I transformed this integral using u substitution into a different integral. My transformation made this. The transformation happened and I have, what function do I have? 1/2 u, right? No, 1/2 1 over u. What was my transformed function inside of the new integral? This, right? 1/2 times 1 over u from 7 to 8. So if I plot this function, it looks like so. Let me do it from say 5 to 35 in terms of u. So this is how it looks from 5 to 25 in terms of u. We need it from what number? 7 to 28. What I'm claiming is, you guys wait, don't go. Let me finish the idea. Why so impatient? Good. What I'm claiming is, when we were finding the area instead of this awkward integral, instead of this awkward area, we decided to convert it to this new shape. And we're looking from 7 to 28, right? From 7 to 28. Now this is a new shape. And we knew this shape. We knew how to deal with this one. Say this is a measuring cup, so we figure out. The claim is, this is the same area. They're the same. So u substitution, u sub is a transformation. It's not only undoing chain rule, but it's also transforming complicated function into a simple one, helping us to find area, but now it's from 7 to 28, of an easier integral 1/2 1 over u du versus x plus 3 x squared plus 4x plus 7 dx. And these were the same. That is the idea of the transformation. Moving around areas in some kind of shapes we know. And in this case, logarithmic function, we knew it, so it worked.
Much smaller value over much larger distance.
Yeah. What do you think? It's pretty fascinating. These topics are usually fun ones, so you have to practice a lot, and then you become pro at this. Thank you. Good job, people. Ask questions if you want.